brief review. Oh, you get notified. And switch those letters there. Review. Related to parametric equations. Parametric. So remember, when we have parametric equations, we usually have at least 3 variables. And for us, we've been doing 3. So we'll have some parameter, perhaps it's t. T could be time or an angle. And then we have x and y. X and y. And problems I'm thinking about when I make these comments are things like the cycloid, an ellipse, circle, ellipse, pretty much any curve really, but those are what's in my mind right now. When I'm thinking about the cycloid and the ellipse, most of the parameterizations we make allow us to go through one period of a regular trig function, and we get all we need to see. So one period. So example of a cycloid, we looked at a cycloid from a circle of radius 1. And we got x as a function of t is t minus sine of, sine of t. And y as a function of t was 1 minus cosine of t. If we used a bigger circle, then all that happens, so if we cross out that 1 and say put a circle of radius 3 and we roll it, that just multiplies out our x and y values. So these just get multiplied by 3. And sometimes you'll see the 3 written as a factor. Other times you'll see it written as 3t minus 3 sine t. Okay, so it depends on where you see the problem, how it's written. That doesn't change that a circle completes 1 revolution in 1 period. So 1 period is 1 revolution. All that changes is how we see it on the x-axis, so and the y-axis. So whereas if let's say this is 2 pi right there, the first radius 1 circle is going to give us a cycloid that looks something like that. Okay, so that's radius equals 1. It's going to go all the way up to y equals 2. But if we take a circle of radius 3, that's a way bigger circle. Okay, it still makes 1 revolution from 0 to 2 pi. So if they were spinning at the same rate, they would start and end at the same rate. However, a bigger wheel will roll farther with 1 revolution, right? Because it's got a bigger circumference. So it's going to be 3 times farther out. So 2 pi, let's see, what are we going to get next? If I multiply by 3, that's going to be 6 pi, right? So 2, 4, so 6 pi is going to be way out here. A circle of radius 3 will have a diameter of what? 6, yeah, so if that's 2, this would be about 4, and 6 would be about here. So a cycloid from that circle will just be blowing this up 3 times bigger. So it'll get 3 times higher in the middle of its period, and so it'll look something like this in comparison. My curvature is not very good, but bottom line though, everything here happened from 0 to 2 pi for either graph. We just scaled up what happened with x and y. And it takes a little getting used to. The more you graph these guys, the more you get used to. And a similar thing happens with an ellipse. An ellipse can be really big or really small, but the bottom line, any ellipse can be drawn by just letting the parameter go from 0 to 2 pi. Okay, so just keep that in mind with the parametric stuff. On the test, and I keep meaning to put a print version up, but I'm being fussy about it. There is a sample test that you can do here. There's a much longer sample one here. I don't really recommend doing that one, but if anyone's dying for extra practice, there's a ton of it in there. So I put up 13 questions here. I'll whittle your questions will be similar to these. Yours will be on paper though. And one thing to note is as you're going through these problems, you'll see headings on the top like, hey, this is a polar coordinates problem. And as you go through the problems, once you get to a new group, it'll say, oh, now you're doing parametric equations, just to get you in the right mindset. Because if you're doing parametric, but you're thinking polar, all hell breaks loose, right? It doesn't work right, or vice versa. And the same thing will happen on your written test. I will have a section that says, this is parametric stuff. Then the next page will say, this is polar stuff. Conic sections is a blend of everything. So I really, the best I can do there is say conic sections, prepare to do mind shifts, because that one's a little trickier. But I'll try to prompt you so you stay in the right frame of mind. Hey, now we're doing polar calculus. And then eventually I'll say, oh, now we're doing parametric calculus. So keep in mind when you're looking at a page, which system am I in? Am I rectangular? Am I polar? Am I parametric? Am I normal? So, all right, let's do some other stuff. Let's see, what do they have in mind next? So we'll do more review tomorrow. We're gonna pretty much wrap up, I think, what we need to do with conic sections today. So conic sections. And I talked the last couple of classes about how conic sections come from cones. I mentioned definitions of conic sections related to a focus and a directrix. So we have their evolution from cones and slices of those cones. And then we have the idea of focal points, foci, and directrixes. What's the plural of directrix? Directrices? Huh. I don't know. We just say directrix. And then 3, we started looking at the end of class the other day, the idea of eccentricity as a measure of determining which conic is which. Eccentricity. Okay. And eccentricity is what we're going to spend most of our time with today. I'm not going to do too much more with the foci and the directrix, except to look at the focus points of ellipses because they're pretty powerful. Eccentricity E is defined to be the distance to focus divided by distance to directrix. All right, let me find my examples and my notes. That one right there, maybe. Definitely need that one. Somewhere I'm missing a page. All right. So for classification of eccentricity, I mentioned this the other day, if E equals 0, oh wait, that denominator's not right. What should that be? I did not write that correct. Yeah, it's definitely got to be the nearest directrix because there can be more than one, but something else doesn't look right there. My notes are kind of messy here. Oh, that's right. Okay. I don't know why it looks funny to me today. All right, so this would be a circle. If the eccentricity is equal to, let's see, 1, it's a parabola. Oops, parabola. If the eccentricity is between 0 and 1, oops, wrong order, then it's an ellipse. And If the eccentricity is greater than 1, then it's a hyperbola. Hyperbola. And a common equation, the eccentricity comes up most often when we're looking at the polar form. So I'm going to give you the polar form and we'll play with it a little bit. And these have with a focus at the pole. Does everybody remember what the pole is for polar stuff? It is the origin. Okay, so the pole in polar is the origin in rectangular. And they tend to look like this. R is equal to some number k, and there we'll come up with some expressions for k in a little bit, divided by 1 minus, or it could be plus, let's go plus or minus, the eccentricity times the cosine of theta. And sometimes there'll be a sign in there. So that could be just, so this would be a horizontal orientation. You could also have k and then 1 plus or minus the eccentricity times the sine of the angle. And that would be a vertical orientation. So we'll just graph a few of these and see what they look like there. Some other tips I had about these guys. Where did I put you? Oops, not too far. Yeah, and with the plus on these guys, thinking about an ellipse, for example, any new color. Come on. With the plus on these guys, the directrix would be on the right. Directrix on right. A minus would put it on the left. These guys down here, a plus, the directrix would be above. And a minus, the directrix is below. And sometimes that'll matter for consideration. Most of the time it doesn't really matter. So if you have a polar grapher, let's mess around with some numbers, see what we get. So I think I will use Desmos. It does polar graphs way easier. And so, for example, if I took a look at R equals, let's try 5 divided by 1 minus 0.5 times the cosine of theta. What we should see is that this is a horizontal ellipse because I'm using cosine. One of the foci is over here at the origin, the other foci is over here, and the nearest directrix would be somewhere over here on this side, on the left side, because I picked a negative. Okay, if I switch that to a positive, and we'll see the ellipse shift over to the left, putting the focus here, and the directrix is going to be over on this side and generating it. And because I have a fraction between 0 and 1, it's going to give me an ellipse as opposed to like a hyperbola. If I made that a 1.5 instead, then it's going to jump into hyperbolic space there. And so we get a hyperbola with asymptotes running through. Now, as far as the hyperbola is concerned, remember lines are a pain in the butt in polar, but the equation of a line is kind of similar to the equation of a conic section. Remember when we generated the equation for a line a while ago? It looks a lot like this. And I mentioned before, lines are considered to be degenerate conic sections. Okay, because if you look straight at a pair of intersecting cones, straight on, they look like this if you can't see their 3D space. Okay, so if you slice down perpendicular to the direction of the cone, let's see, I got that right. Parallel to the way, yeah, if you go parallel to the way the cones are opening up and down, then and right through the center, then you get a pair of intersecting lines instead of something like a pair of the hyperbolic curves like that. So lines and circles and conic sections are all related polarized, which is kind of wild. Let's go back. As far as the eccentricity, if I pick an eccentricity of 1, then I get a parabola. If I pick an eccentricity of 0, the cosine is gone, and I now have a circle of radius 5 in this case. If I pick a radius of like 0.1, then I get a more circular ellipse. If I pick a eccentricity of 0.9, then I get a much more elongated ellipse. Okay, so the closer the eccentricity gets to 1, the narrower, you could say, the longer the ellipse gets. The closer it is to 0, the more circular it is, and the foci are sitting right up next to each other, really tight. Okay. All right, so let's play with some problems. What did I have in mind? That was a nasty problem. We don't want to do that one. We're not quite ready for that one. Not quite ready for that one. We'll get there. Okay, let's do this one right here. Let's consider new page, new color. R equals 6 over 7 minus 5 cosine of theta. So first thing we want to do before we graph it is see if we can identify what kind it is. And so one thing I'd like to do here is I could say like factor out that 7 from the denominator, or we could multiply top and bottom by 1/7, which is a little easier algebraically. So if I do that, then I could also think about this conic as being equal to 6/7 divided by 1 minus 5/7 cosine of theta. So what does this tell me about it? This tells me a couple of things. It tells me this is oriented horizontally. And the horizontal orientation tells me that both foci would be on the x-axis. I don't think that has 2 eyes. On x-axis. The negative tells me that the directrix is to the left. And that tells me that the left focus is at the pole. It's an arrow there. Left focus at pole. All right, so let's play around with this thing. So I'm just going to estimate its graph here, and then I'll use GeoGebra to double check. So I think one focal point will be here. The other focal point is going to be, I'm just going to guess, throw it there. And so then this thing is going to open up around those somehow. What I'm not quite sure of yet is the scale vertically and horizontally on these. Okay, I don't have those nailed yet, but we'll figure that out in just a minute. So our goals here, what I'd like to discover for this particular graph is what are the intercepts And can we come up with the major and minor axes? So I want the focal points, so foci and major and minor axes. Is what we'll play around with. So let's graph it on a computer grapher. Desmos will work. So let's see, what did I start it off with? I had 6 in the top, and I had a 7 minus 5. And zooming in, so I can see its horizontal orientation. I have one focus here, the other focus lives somewhere over there. We're going to want to find that. We're going to find these intercepts and those intercepts here. A note on this right here, an idea I haven't talked about yet that is in the book. When you draw a vertical line or horizontal, depending on the orientation, through a focus, you get this line segment right there. And that line segment right here is referred to as the lattice rectum. And it turns out in the previous version of the formula here, that K is the length of the lattice rectum. Okay. And there's a couple of different ways you can calculate the length of the lattice rectum, and we'll look at that shortly. All right, so let's get back here. So some things I want to check out here. My rotation, what's going to happen if we check this out and we plot theta and r, if theta is equal to 0, what happens? Well, cosine of 0 is 1, so I'll get 1 minus 5/7, which is what, 2/7? 6/7 divided by 2/7 is 6/2 or 3. So I'm going to get a 3 there. And if I'm going to jump all the way over to pi on the other side. So that's this point right here. If I plug in pi, I'm going to leave a little space. Cosine of pi is -1. So then I'll get what? I'll get 1 plus 5/7, which is 12/7. So I'll end up with 6/12 or 1/2 there. Double check with Desmos. And remember, Desmos has a problem. It can't plot polar points, which is kind of trouble. But if that's -2, then this must be -1, and that must be -1/2. So it looks good there. Okay. So in order to get points out of Desmos, we would have to jump to parametric. Everyone remember that? Which is kind of a pain. So sorry, I don't have an easy solution there for you. Okay, so let's do a couple other points. So this right here happens, that's a radius of 1/2 out there, and theta, or yeah, we're using theta here, is equal to pi. At pi over 2, pi over 2, I should be up here at the top. And so for pi over 2, we get 0. And so I just get 6/7 over 1, or 6/7. And that's 1 pi over 2. 2 pi over 2 is pi. 3 pi over 2 puts me at the bottom here. And so again, at 3 pi over 2, cosine is 0, so I get 6/7 again at 3 pi over 2. So this point up here on the x-axis is 6/7, and that point down there is also, that we call that -6/7. For y, although r, since we're pointing down, is still positive. So we got to keep our brain straight when we're referring to r, when we're referring to x or y. Usually when we talk about intercepts, we're talking about x and y. So here's what I believe the intercepts are for part 1. The first intercept I found was 3, 0. If I go in order, the y-intercept at the top, that would be 0, 6/7. Next one over here would be x was 1/2, y was 0. And then where are we down here? We're going to be at 0, -6/7 for y. So I've got the intercepts. Jumping for a minute over to part 3, often there's a difference between a major axis and a semi-major axis. Okay, so I'm just going to jump to a new page to talk about that a little bit. -1/2, correct? Yes. Let me fix that. Thank you, Clint. Let's see, back. That should be a -1/2, 0. Yep. -1/2 for x. And I often want to remind myself what I'm referring to. Like here, I could consider that the point where r is equal to 3 and theta is 0, but it's also the place where x is equal to 3 and y is 0. Okay, so let's do a quick picture of that again. So let's say that's -1, +1, +2, +3. 6/7 is almost 1. So if that's 1 and that's -1, -1, 1, 3. Then again, I have points about right here, right there, right there, and right there. So the major axis here, and I'll plot some more points in a sec. Major axis. Well, that would be just the difference, the distance between these 2 points on the x-axis. So my major axis is going to be equal to 3 minus -1/2, which is just 3.5. Or what, 7/2? Often what we want is the semi-major axis, because that's useful in rectangular coordinates. So I'm just going to make a note here that the semi-major axis, it would be half of this length, or 7/4, right? 1 3/4. One thing that's a good thing to know is now I can identify the center of the ellipse, because an ellipse does have a center. It's the place where the major and minor axis meet, right between the focus points. Now, I already know that one focus point is here. If I can find the center, I can find the other focus point. Okay. Other way to think about it, if I know the difference between a focus and its nearest vertex, then I must know the difference on the other, the position at the other side. Right? So if here I have 3 as the vertex and the distance between this vertex and this focus is 1/2, then at 2.5 must be the other focus due to symmetry. Just to double check on that, I'm going to note the center of this circle. So the center of this circle is going to be 1 3/4 units away from either vertex. Okay, because that is the length of the semi-major axis. So if I take 3 and I subtract that 1 3/4, then what's that going to give me? 1 1/4 or 5/4 should be the central x value here. And so let's check that out. Let's see, that would be 1.5. So 1 1/4 would be right about here. So that right there should be my center. Double checking the distance from, did I do that right? Yeah, yeah. So the distance from this focal point to there is 5/4. And then if I take 5/4 plus 5/4, that's going to give me what? 1.5, 2.5, which puts me at this focal point right there. Okay, so I'm just identifying that, yeah, this is in the middle of everything horizontally. Okay, so I'm sure about my focal points now. So now I can go and answer question 2, which wanted the foci. And the foci are the points, that's a colon there, 0, 0, and then 2.5, 0. So I have two ways to proceed from here if I want to find the minor axis. Okay, minor axis is on this line right here, wherever my ellipse intersects up here somewhere. And so here's my ellipse, something like that, to the best of my artistic ability. And the minor axis is going to be the distance from this point to that point. One problem I have right now is I know where this line is. Lines are kind of a pain in polar. And so in order to find this in polar, I would have to identify that angle right there, which means I have to identify that line, put the line in polar, find the intersection point, which is like, oh my gosh, that's a nightmare. But we do have a trick up our sleeve from rectangular. From rectangular, we found that there was a relationship between the semi-minor axis, the semi-major axis, and the distance from the center to the focal points. Okay, and that relationship existed when, I'll use my highlighter here, when we drew this triangle right here. Okay, so what we're going to do is we're going to analyze that triangle, and that'll give us what we want. So we want this triangle right here. So this is my half the distance between the foci right there. This guy right there happens to be the same as that right there. That's the semi-minor axis, or semi-major axis, sorry. And we have all of that information right here. So we know the distance between half the distance between the foci is that 5/4 that we calculated, because one of the foci is the pole. Okay, so just isolating that triangle there, I know that the bottom here is 5/4. The semi-major axis is we calculated to be 1 3/4. Okay, which is 7/4. So that's right here, 7/4. And so this right here is my semi-minor axis. We usually call that guy B. So now we can calculate that pretty quick. So we know that B squared is going to have to equal 7/4 squared minus 5/4 squared. So one thing that you'll probably get the point pretty quick is the last couple of days, we're just doing tons of geometry with some graphing along with it. So what do we get there? We're going to have 16ths, right? And then 49 minus 25, 24. And that cleans up a little bit. What, 8 goes into both of those? 8 goes in, what, 3/2? And so that's our B squared is equal to that. So our B is the square root of 3/2. And a lot of people like to rationalize the denominator. You know, I guess we could, but I don't see too much point in that. It doesn't really help much. But let's double check to see what that's like. Anybody calculator, what's the square root of 3/2? Let's see, SQRT of 3/2, 1.2-ish. Okay, so looking at my GeoGebra graph, this would be 1, that's 1.5. So yeah, it goes about as high as 1.2 from the axis. That looks reasonable to me. We're in the ballpark there. All right, so a little bit of blending rectangular and polar coordinates there. What else looked interesting? I'll leave that one for you to think about. Let's try, I thought I wrote down another cute one. Oh, some relationships that I think are helpful. Let's write these down. So, ellipse parameters And there's so much amazing geometry around conic sections. So we have a couple of different versions of our ellipse stuff. So one is considering that in polar, what we generally do is we have one focus at the pole. A circle has a single focus, it's called its center. A parabola has a single focus. Ellipses and hyperbola, they each have two foci. So if I'm thinking rectangular, then for an ellipse, with a focus at a pole would look something like this: x plus c squared over a squared plus y squared over b squared equals 1. And we played around a little bit with that idea yesterday. We first looked at an ellipse centered at the origin, then I shifted that ellipse over to put one of the foci at the pole, at the origin. So a related equation to that is the polar version, which for this would look something like r equals k divided by 1. Let's see, since I have a plus c there, I would go plus the eccentricity times the cosine of theta. So this would be the related equation there. And so then the question is, okay, well, how are K and E related to A, B, and C? Okay. And so that there's a lot of different ways to play around with that. I'm going to just give them for now, and maybe I'll elaborate on some of them tomorrow. The eccentricity can be found by taking C and dividing by A. Keep in mind here that we have the relationship that C squared is equal to A squared minus B squared. With an ellipse, A, the major axis number, is always the biggest number in that triangle. So we could also say C is equal to the square root of A squared minus B squared. Another useful number is the distance from the focus to the directrix. That's usually called P, and P is B squared divided by C. Let's see. Then we have that lattice rectum. And the lattice rectum, remember, is the distance cutting through a pole or cutting through a focus. That's usually referred to as L. In the equation up here, I'm referring to it as K, but in most books, you'll see it as an L. And L is equal to B squared over A. Other ways we'll see that is it'll also come up, and you can do some algebra based on this, that it's, if you screw around with these variables, you see that it's A times 1 minus E squared is another way you'll see that length of the lattice rectum. There's another distance that we'll see sometimes. Distance, let's see, from a focus to a pole. That's usually given the letter D. And if we consider that, then yet another way to refer to the lattice rectum, which is the numerator of my polar thing, that's why it's so popular, it's the eccentricity times that distance from the focus to the pole. And for some reason, I always liked this one the best. For two reasons. I think it's the simpler of the bunch, and I thought it was always cool that it's spelled Ed. So my favorite representation is to write this as the eccentricity times the distance from focus to pole over 1 plus e cosine theta. And so the way I have all these guys oriented, all of these are analyzing, and these relationships here really don't change anything, but my plus c here and my plus e cosine means that I have the right focus at the pole, and because I'm using cosine, my foci are horizontally oriented, not vertically oriented. So this equation here and this equation here would lead to ellipses that look like that. These relationships down here, doesn't matter whether it's horizontal, vertical, sine or cosine, these guys down here are always the same. Okay. So we're running out of time. The problem I wanted to do next was going to be exploring this geometry a little bit, and we'll have to do it tomorrow. The problem I wanted to look at is when one body orbits another body, it does so in an elliptical path. And usually those elliptical paths are roughly circular. And so the foci aren't usually too far apart. Okay, and so maybe this focus right here is the center of the orbit. Okay, so perhaps there's a planet sitting here, and then there's some satellite out here orbiting around. And often parameters that are interesting are like the apogee and the perigee of the orbit. And so when is it closest, and what is that closest one? And when is it farthest out here? And it's kind of cool that if you know what its closest position is and you know its farthest position is, you can derive the whole equation for either the rectangular or the polar version of the conic. So we're going to attempt to do that tomorrow. I meant to do it today, but we're out of time. And we're gonna rely on these algebraic relationships to help us figure out what those values are. So there's going to be a little fun arithmetic and algebra jiggery pokery with that tomorrow, and we'll take a look at the idea of orbits. And I'm going to focus on near-Earth orbits, but it doesn't matter. There's not much difference between a near-Earth orbit, a far-Earth orbit, or a close-Earth orbit, or a near Earth, middle Earth. Yeah, they categorize them in different ways. And my belief is the categorization, somebody just decided, hey, let's let 4,000 kilometers be the difference between near Earth and middle Earth. Why 4,000? Ah, that's a nice number. So we'll play around with that tomorrow. Okay, so let's see, Clint, let's test out you on